That's true, yeah. All right. I'm all for it, it's like, I'm stuck here. All right, so it's recording. So anyway, yeah, I wanted to go through that. So some two groups actually solved that problem on how to do this one, equation 12, whatever. Yeah, equation 12. So we do it. Oh, yes. FIG is 1 minus so oh, project. This goes on. False focused. All right, so see, have that scheme. So it's got nothing to do with the D, whatever he said, the aspect ratio was proportional to D. That's got nothing to do with it. So so you have this intergranular region and then the middle. So the whole thing is like you have to define that as D. Like the whole thing, So then and then define this as T. And that's just D minus T gives you the area of that one. Yeah, that's true. I mean, there's a problem with when 1 minus that gives you the intergranular fraction. All right, but that isn't really logical to do, because all right, so for one thing, it's not really a sphere with a shell around it. It's like these kind of domains or grains or something. I don't know. So you have all this. Anyway, it's not, doesn't look right to me to do it that way, but anyway, that's how you got that equation. And it's pretty simple, actually, but doesn't seem right. Anyway, so two groups figure that out, 2 or 3 or something. So it's possible to do it. I didn't. And all right. So then I wanted to finish this. Why is that like that? So I want to kind of finish this section, and then you go. Chakwu Okali is going to come in and kind of help with the other thing because he's been doing the lamps thing. I mean, I can go through it, but he might be better. If he doesn't better, then I can just do it. The last one, so the last one you can't exactly do in Windows. The 6, there's like 6 things, and the 6th one you have to compile it. So you can do it on a Mac, or you can load Linux and compile it. So, and then you can run it on Windows after. So you don't need to do 6 in the last one. If you want to do it, you can, but anyway, so we were kind of going through the like all the different methods of simulations. Yeah, you don't need to do 6. The 6, the 6th one and the thing. Yeah, because you need to recompile lamps, and you can't do it unless you're using Linux, or a Mac will do it. Yeah. So all right, well, they should have emailed, I guess. I guess someone emailed me and it was like, what you just said, So, so you guys already got 1 to 5 running, or? Yeah. Oh, okay, that's good. So,
well, basically, it's just force simulation, right?
Yeah, the first one is just get the lamps thing up and running. Yeah.
You just need a screenshot of that, just to show the command window.
Well, if you do the other ones, that one's already done, I think. You couldn't get the other ones without doing that one, so. Yeah, hopefully it won't be too bad, and it'll be kind of like fun to do, but it didn't seem like it was fun to do from the email I got. Which was like, I'm at wit's end, something, yeah. So anyway, let's see, if I can get back into this thing. Anyway, why don't I just go? So there's different kinds of simulations. That's basically the idea. So coarse grain. So the small scale would be like quantum mechanical for kind of electron density calculations, kind of molecular scale. If you want to know band gaps and things like that. And then the next scale is this kind of molecular dynamics where you put in molecular dynamics you can run with wave functions, or you can do it with like a 612 potential for atoms, or you can do it with kind of coarse grain, just spheres, and then whatever interaction thing you want. So the coarser grain you get, the more kind of simplification to the equations you have. And then so basically molecular dynamics kind of cuts across this whole range, and essentially you just use different potential functions. I mean, you can do something like molecular dynamics using the quantum mechanic wave functions. So that's what, all right, so it depends what you want to get out of it, and also kind of what you want to get out of it has to do with the size scale. So if you want to know the band gap, then you need to know the electron structure. Then kind of a coarse grain simulation isn't going to do you any good. If you want to know how liquid crystals work, you need this mesoscale. You can't do it with wave functions. And so that's kind of the scenario of it. So molecular dynamics is one of the tools, and the other main tool is this Monte Carlo thing. So we've gone through Monte Carlo a couple of times, and you can do Monte Carlo also with wave functions. You can also do it with kind of 612 potential kind of setup, or you can do it just with magnetic dipoles, or any kind of dipoles, or any kind of orientation. So you can do Monte Carlo with a lot of different things as an input. It's just kind of a technique. It's like a mathematical technique to simulate a thermally activated process. So you have this kind of random kicker in there that allows it to thermally activate. If you change the temperature, that kicker choice changes. So it gives you thermal control. So it's basically a thermodynamic modeling process using the Boltzmann function as a weighting factor. So then it's mostly bookkeeping, right? So like this is an example of the kind of bookkeeping you have to do. And with any kind of bookkeeping like this, you have to chop it off at some point. You can't just keep going. You'll get too many terms to calculate. This is like a potential. It's a potential between 1, 2, so binary potentials, and you have 4 atoms. So you have like how many do you have? 6 potentials for the 4 atoms, binary potentials, and then ternary potentials. You can have more, and then you could have higher and higher order potentials if you want to add them up, right? So you get to have more and more terms to deal with and then like in this simulation, we get to the polymer part. So you'll see like he goes through a single particle with no interactions is floating around doing Brownian motion. That's the first one. And the second one, there's some potential between the particles and Brownian motions. It's like 100 particles in a box moving around. Then he glues them together into a polymer. Right. And then I think the fourth one, he puts stickers on it so that they can stick together and kind of collapse. As you can see, kind of a structural transition. So anyway, these are just, this is an energy, and then there's a spring constant energy. So kx, and if you integrate it, it's x squared by 2. So you get this kind of function. If it's an angular spring constant, then you have that function. Then this is a Coulombic potential energy. So these are just all the terms you learned in physics, whatever. Like Coulombic interaction energy is this. So you just take all the terms you used in physics and just plop them in here, right? Or physical chemistry is kind of the 612 thing. So it's just, these are all like textbook terms. So there's nothing really new about what's being done. Like they're just adding together all the terms from the textbook and then just letting it cook on those. Like it's going to just take time steps. Then you're going to have the position, the velocity, and then the interaction energies. You're going to just let it, so the particle is going to move, that's going to change their positions, and the energy of interaction is going to change because these separation distance, like R, is going to change. So the spring constant would change. And also the R's here will change too. So basically the 612, you'll be moving around this potential well, they have a spring involved. So you just add up all these components, right? So it's kind of a simplistic disassembly of the world by the terms that we know would combine to them, would create that stuff. Then, so we're up to 18 here. I kind of went through the Monte Carlo thing. I think I already mentioned it earlier with magnets. And then let me go to 18 here. So this is in the book. So the reason this is here is because it's in the book, basically. So basically, this is kind of a molecular dynamics approach where you're using some wave function to talk about in other words, you're looking at electrons. So it's below atom level. It's like how the electrons interact. And then the nuclei are seen, because the electrons are flying around like crazy, and you see the nuclei are just fixed in space. So they're just spots with charges. It's like little charge wells. And the electrons are kind of bouncing around those bumpers, like a bumper pool kind of thing. Right. So anyway, the electrons are quantum particles, so they're going to follow like Schrodinger equations. So they aren't going to have any possible energy or any possible position. They're going to have to follow these wave functions. So in order to get the energy from the wave function, use the Hamiltonian. This thing's going to be broken into these four terms. So first, this is a derivative, a spatial derivative, like d wave function squared. So the wave function has to be squared because it's got like plus and minus values, right? So you have to have it squared, dx squared, dy squared, dz squared, right? That's the del operator. This is like an operator on this wave function. So that's going to give you like the kinetic energy, basically the 1/2 mv squared kind of thing. But the second derivative is going to give you the kinetic energy of the particles, and then there's Za is the potential on the nuclei. So this is the nuclear interaction potential, and this is interaction of the electrons wave function with the nuclear potential. And then this term, this is a repulsion of electrons to electrons somehow. Not sure how that works. Oh, because you have the wave, you're operating on the wave function. So then, so the wave function just multiplies by this. And this is the nuclei, so that's like a constant. Nuclear repulsion. So from that you can calculate the energy. You're trying to minimize this E for the system to get this, so you iterate this thing until you get E to have a minimum. And then that gives you this ab initio. It's really a calculation more than it's an iterative calculation, right? So trying to minimize the E here. So this is in the book, that's why it's kind of here a bit. Then people talk about density functional theory. So you're going to have, again, it's talking about electron density. So density and density functional theory is electron density. And because for a complex system, you can't get so the Schrodinger equation is good for like simple systems. But when you have crystal systems, you can't exactly get the wave function. So you calculate the electron density, which is a thing you can observe. So you can't observe the wave function because it's got an imaginary number in it, right? So you have to square it to get the density. Then you say that your energy is going to be a function of the density. So, and the density is a function of position. So that's a functional, I guess. A function of a function is a functional. So you have the energy is a function of the density, which is a function of the position, which is a function of waveform, which is a function of the position. And so everything's a function of a function of a function of. But you don't know this thing. This thing could be measured, right? So So anyway, this is also an iterative procedure to try to guess at the thing you don't know, which is the waveform, right? To kind of get them minimize the energy in the system. And then it's also going to be a sum of energies. You have sum of the kinetic energy. It's the same sum that we had. Kinetic energy of the density of the electrons. So these are the same things, except this last thing is called the exchange correlation energy. So that's that should be explained here, except it didn't give me the new set of slides. But anyway, so this exchange energy is because the electrons are you can have more than one electron that has the same energy level. Like I guess you can have two, so they can swap each other. And there's an energy involved in that swapping. That's the exchange energy, exchanging the electrons. And the correlation energy is the energy, let's see, it's the interaction energy between the electrons in the electron clouds. So this whole term you don't know, but it's a constant. So that ends up being like, how do you solve that is kind of one of the main issues of density functional theory, this exchange correlation energy. This is what, slide 19. How come I don't have the new version of this and I just updated everything? Oh, let's see. This one will probably be the new updated version. No, it's the same thing. All right, sorry. I definitely put the updated things. Anyway, so that's all I'm going to say about that. I don't know much about density functional theory, but basically they're all kind of iterative processes, right? So anyway, so we have lamps. That's the thing that's easy to use, not involving quantum mechanics, right? So you've already kind of seen that if you started doing that problem. And then so you can run it on your laptop, or if it runs too slow on that, then you can get free access to graphic process units from Google at this web page, or you can use the Ohio supercomputer to upgrade whatever you're doing. And then Hamid Blues, and so there's a bunch of different options to lamps for molecular dynamics. So it's going to be either you can do lamps won't do waveforms things, but it'll do molecular scale molecular dynamics, and then it'll do these coarse grain molecular dynamics. And of the coarse grain molecular dynamics, so you can go to different, so you're clustering together atoms, right? And then saying that that group of atoms is a sphere and it's got an interaction energy you could calculate somehow from the original group of atoms. So you can figure out the potential of it from what you started with. So anyway, so basically the potentials you use, you just choose in the LAMPS program, right? Like we had I mean, in the homework, you're just using Leonard Jones potential, which is a 612 thing. But you can put in any potential you want there, right? So one of the popular ones is this DPD potential, which is going to have like this kind of 3-component setup to it. So it's got oh hey, how you doing? So anyway, conservative, so you have basically the 3 components of the DPD: conservative force, dissipative force, random force. All the potentials are going to have a random force because that's the temperature, but that's a random motion of the atoms with temperature. So basically you're doing your time steps, and once in a while it randomly kicks it. And the amount that it kicks it is going to be related to temperature, right? So you're running the thing at a certain temperature, so you're doing this kicking process, and that's what this thing is. Conservative is going to be like a spring holding the things, like the interaction potentials, like Leonard Jones, and then, but in this case, this conservative is going to be like a simple, and the dissipative is going to be like a friction type thing or drag coefficient, right? So here the conservative isn't going to be 612; it's going to be a simpler function. It's going to be just a linear function in position with a cutoff distance. So you're only going to have interactions over a certain distance. Instead of that well kind of thing, it's just going to be a linear decaying potential between the particles, right? So that allows you to look at much larger systems, and the 612 is more calculations. Just makes it's simpler to do large systems. And then the conservative is basically a spring constant kind of function here someplace. Well, that's a conservative. Then the dissipative is a drag coefficient thing. So it's like the velocity times a drag coefficient, more or less. You have the velocity Bij times a kind of a drag coefficient. That's got some spatial dimension to it. And then the random force is this theta is a white noise function. So that's just a yes, no, 1, 0 function that pops up randomly. And it can be positive and negative. So it can kick the thing forward or backward or either sideway. Right. So basically that's the kicking function. So these things are all like, so you just say you're going to do DPD in the lamps thing. This stuff is already coded. Right. Like someone said, like, I don't know, I never took a class in computer programming. I mean, I ran into someone that was working for Jim Marks who was doing a lot of computer simulations, right? And then I had it in the class, we had like an actual coding project. We had to write a program to do something like, I don't know, just a loop thing to do something. And she couldn't do it at all. Like she didn't know any programming at all. Yet her whole PhD was on this kind of lamps stuff, you know. So you don't need to know how to do any programming at all to do this, because all you're doing is writing a script to call commands. It's essentially just running a software, but it's a little bit more complicated because you look at, and you have to know the terms. So if you get the terms wrong, it won't work at all.
I'm trying to make it work now.
Well, ask around. I think a lot of
Yeah.
people, anyway, Hugo's here. He can help.
Oh,
Yeah, he's the expert. So he can help. I can help a little bit. Basically, if you get the words wrong, the words have to be exactly the same. You know? So it
yeah,
only,
I changed, I got it to the right directory. And then it's on the website, it says make MPI or serial to compile it,
Okay, do you have seen?
oh, for number 6?
just to get it to work.
Oh, for the first
For
thing?
installing.
Oh, okay. Yeah, Hugo can help with that.
For 1 to 5, you might just download the already compiled one. But for 6, you have to include the first field in the source folder and recompile it.
Okay.
Yeah, so now.
Yeah, but he's trying to just download lamps, period.
You don't need to do that.
He's going the long way for the number 6, which is okay. If he does what he's doing, he will be able to do 1 to 6.
Okay.
Fantastic. Do you have CMake installed?
No,
CMake. Okay, just go to your terminal and type
Yeah.
CMake. Just open it and you'll see whether it's installed. Then after that, I'll come up.
okay, we can do it after. I
Okay,
didn't mean
yes.
to interrupt.
No, that's all right. Yeah. That's kind of the point today, is just to get that thing running if you have problems with it, you know. I mean, all right, I want to go through some kind of stuff too, I guess, but yeah, it's just kind of like, I mean, all these things, so DPD is just using different potentials, but the same thing, like in this program, if you look, it's going to say like the initial positions. So first thing, like if you have more than one particle, it's going to say like, what are the positions, X, Y, Z. So Cartesian coordinates. Then it's going to have like 3 zeros, which are like, that's the place where because so you have a box and you have kind of a lattice for the part. So there's no lattice, but so you have a box that's holding the particles, right? And they have X, Y, Z positions within that box. When they get to the edge, they're going to come in the other side. So it's got this like reflection thing at the sides of the box. So basically, so you have 3 numbers for the X, Y, Z. Then you have 3 numbers that are like how many times it crossed the border of the box and came back in the other side. Okay, so like, and then after that you have then it's going to list the velocities of the particles, which at the beginning they're all 0. Like you start with 0 velocity, right? So, and then what else? We can go through one of the setup files for the thing. But it's the same thing though, like define initial positions and velocities. That's everything you're going to do with molecular dynamics is going to be like that to start with. And then calculate the forces. So that's the potential function, whatever function you put in. So it could be 612. So if you're using Leonard Jones, it's going to be the 612 potential, and then the spring constant, like a couple other terms that are just common terms, right? So if you know the forces and you can get how the forces create, so mass times velocity is a force. So you're going to get the force and the velocity are related to each other. So basically that's going to change the change the velocity of the particles for the next time step. So the first time step, you're at a position, you have a velocity, you take that delta t times the velocity is a change in the position of the particle. You add that to get a new position, then the forces are going to give you like a new velocity for the particles at the new position. They just go through another, then you loop through, is at the end, no, go back and do it again. And then additionally, there's going to be a thing like output the whole array of the particles every once in a while so that you can see, so you can make a movie of it after. So if you're going to do 10,000 steps, you don't want 10,000 frames, it's too many. Say like every 1,000 frames pop out a picture, which is just going to be an array of numbers. It's going to be a list of all your particles, 1 to 400, and then like XYZ of where they are in their velocities, and then how many times they cross the border. As how many times they reflected and were reborn on the other side. It's kind of like a rebirth kind of thing. Anyway, so that's how it works, and just runs until it stops, right? And then you look and see, because you know 1/2 mv squared is kT, then you know the temperature. So you can see for the whole system, if you add up all the 1/2 mv squares, you can say what's the temperature of the system. When you start out, the temperature will be like high, then it'll decay down and it'll plateau out over time. Once it reaches a plateau, you're done. Like you've reached equilibrium, or quote unquote equilibrium. Like I said before, you never know if you reached equilibrium because you don't know what you're doing really. It's just a black box that you're throwing stuff into. But you say, because it plateaued out, it looks like equilibrium. So I'm saying that is equilibrium, right? So same with Monte Carlo, you can just do it so many steps until it looks like equilibrium. Anyway, so that all these are kind of the same thing, DPD, Langevin, even if you use molecular wave functions, you're doing it pretty much the same thing. So anyway, so there's lamps, there's a bunch of programs, like I said, there's lamps, Espresso is another one, Hamid Blue, DMAX, there's a bunch of them, right? This paper like compares the different ones. This is a list of more of these kind of free softwares, although GeoStudio isn't free. Lamps is free, all the others are free. And they also, all of the others have people that are like coding it. Like at Sandia, there's people that you can email and they can fix your problems. Like if you have a problem with loading the thing, the lamps, you can email the guy at Sandia, he'll tell you how to do it. You know, and there's a lot of other people like floating around that are messing around with these things too. So like you go, so usually you can find somebody that can help you get the thing to run, you know. So it's not that bad to do if you want to do it, you know, it's definitely possible to do. And it can kind of give some legitimacy to the things you're doing. Like if you can do an experiment, you get some results, and you can simulate it and get the same result or something that looks kind of similar. Then you can show a plot that shows that's how the thing behaves. It just makes it look like you know what you're doing. Like you can put the fundamental equations in, get the same answer you got out of the experiment. It kind of makes it look like you know what you're doing. For problems you can't just analytically solve. Like you can't answer the question. Like you can't answer the question, how does a liquid crystal, where that picture was, but like how does a liquid crystal form, organize itself? Like you can't answer that with the math, with some kind of math functions. The only way to answer it is to let it do it and then see if it does it or not. You have your input equations, out comes the liquid crystal display working, you know, so then you say it's because of those fundamental equations that the liquid crystal display works. And so that's the kind of problem. It's not going to be mathematically, analytically solved. Okay? So you can do the experiment, show that you can get the liquid crystals to align. Then you can do the simulation, show that beads will do the same thing if you put in the right potential functions. And then that gives some legitimacy to your statement that you know how the world works. Might not be true, but so anyway, the other thing is like the biological people, some membranes are going to be using kind of a different set of programs, basically, mostly because water, right? Like water is a strange beast and it organizes around molecules in weird ways, and that changes the entropy and the energy of interaction and stuff. So being able to deal with water And a lot of waters is makes it a lot more complicated than what lamps can do. So lamps can do like water as a background, but it's not going to be able to like tag each water molecule and how it interacts with a protein during protein folding. Right, so special programs like Charm is one designed around like proteins, and there's also visualization programs to look at how the proteins fold and things. I think Chromax is a popular one too for biologists, basically. Although some materials people are using Chromax. I think they're similar to lamps. Like it's going to be the same kind of process. The process being that you're going to get going to have a start file that you have to create somehow. Right? So you're going to have like some kind of let's see. So get rid of that. Yeah, so here's this like see this like a typical start file. So you just saying you have this is the input thing you're going to put in. How many atoms? One atom. How many atom types? One atom type. So the atom one, the label one, and then has a mass of one. Then the atom's position is 000. So XYZ is 000. And how many times did it cross the border of the reflective box? So it hasn't crossed the border if you just start it. So 000. And then this has no velocity in it in the input here. Normally it'd be like velocity is the next thing, right? So that guy, so all your input things, so you can have two files, like so however you make that. So if you have a more complicated thing, like you have 400 atoms, right? And each has an XYZ, and they can't overlap. Like you can't have an atom on top of an atom, right? So it's going to be hard to make that. So instead, you just say like the atom types. You have one atom type, so you could have two atom types, and then the second would be one or two, right? So first one is the atom number, like the identifier, the name of it. Then what is it? It's a one. Then where is it? XYZ. How many times does it cross the border? 000, right? For 400 of them. Then like what's their velocities? Initially, they're just sitting there. So you have zero velocity, right? But there's a potential because you're using, in this case, the code's going to use a Langevin interaction. So there's forces. So they might be placed like right next to each other, or some might be overlapping each other, like because you just randomly made that. So you have to first like let it cook a little bit to get them not overlapping on top of each other. Like you have to have a code to make them like move out of the way first, just a warm-up code, like 1,000 cycles of time steps to get them to like move apart. Then they're going to be in some starting position where it's reasonable, like they're on top of each other. And then at that point, you can calculate the force using the Langevin equation, and the force is mass times acceleration. You have a velocity for the particles from the forces, right? And then you can do a time step and move them. Then you have a new set of potentials, and just iterate, like let it loop through that, right? So then it's just a matter of saying like how many times you want it to do that, and how many times you want it to spit out a picture of where the atoms are. And the picture is going to be a movie. So each frame, like you're going to do 1,000 steps and spit out a picture and go through whatever, right? So nice. That's kind of how these things are working, right? So you goes here. So
if you're making your own, like own atom, would you have to define every location? Of every
yes,
single
that's the
particle?
problem. So you have to write another program to define your starting thing. That's a problem. So then it's not going to write that stuff for you. If you buy the studio thing, it will, you know.
We wrote a program that did it.
Yeah, it's not hard to write a program to do it, but you kind of need to write a program, or you could do it manually, but basically, I mean, you're going to be sitting there for a long time. Well, no, the overlapping you can take care of, but still just 400 XYZs that are kind of randomly distributed. Like when he does the polymer, I think they're in a straight line, so that's pretty easy. Just say like glue, 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 all the little beads together in a straight line, then let it warm up, like shake a little bit, and then go into your simulation using that as a starting, right? So the polymer is actually easier, but the particles are harder because they're not in a straight line, you know? So you want them kind of random at the start. Anyway, yeah, you'd probably write a program to do that that's separate from this. So that's a caveat to this. or you can buy that whatever studios one, which is so I don't know, it's 10 grand or something, and then that will make the particles for you. In fact, so if you buy the one, so all the little things that you do to analyze the data, it's like you want to get the correlation function. Well, this will give it to you, but it might not be in the form that you want. So basically you might need to write a program to calculate the correlation function from a 2D array of particles, which isn't hard to do. It's an integral. So you do a numerical integral. But basically, there is some coding in the analysis of it, unless you want to shell out for the programs that do that for you, you know? So depends how much you hate programming. Anyway, so it's good. You want to just go through each of the things in this or something? Like that would be pretty good. Or do you need, yeah, you must know it.
You can tell the computer's running.
Yeah,
Basically, like every time you use this, you're going to start with something that you found somewhere on the internet. You're going to Google lamps and then whatever your problem is. You know, like make a micelle. So you're going to Google lamps, make a micelle. You're going to find a bunch of codes that people have done like this. So these things are available. They can just download, and then you're going to say, well, it's not exactly what I'm doing. But I can change their code a little bit here and there, and then get it to work. Right. So that's the whole. In fact, that's the entire scheme of any kind of programming. Like you're going to basically start with someone who's already done it. Once in a while, you have to do something new, but that's pretty rare. Like almost never. Right. Always, you're going to just say like someone's already done this. I'm just going to modify it a little bit. So that's kind of what you're doing. I mean, that's how programming works. I mean, you can do simple programs like do loop or something, but basically if you want to do something more complicated, mostly everything's already been done. So like why recreate the thing that's already there, right? So anyway, so that's how this works. So what does Leonard Jones units mean? I don't remember that.
attempt it a bit. It's like,
All right.
if you want to run lamps, first and foremost, you have the lamp script file and the initial configuration file. So like Dr. Kwasi said, the initial configuration file is what you're telling lamps where and how your atoms are located. Assuming you're trying to simulate the crystal. In your initial configuration file, you have to define the bond types, how many atoms do you have? You're simulating sodium chloride. You have to tell it atom 1 is sodium, atom 2 is chlorine, how are they bonded together? You have to define all those ones. But since what we're doing are not the complicated type of systems, so just doing particles running around, they can be anything. So they don't have any like bonding between each other. So that's for the initial configuration file, which he showed you now. And talked about that you can have software. So many software can make those systems for you. Just say you click on, they have GUI, graphic user interface. You just click on what you want, the code writes it for you. And so you can even use the C files of these structures to generate the initial configuration file for you. They do a lot of those stuff. You pay maybe for those software, or you write your own code. Then now the lamp script is what? Lamp script, like we are not doing programming. Plants are written the codes for you using C++. So what he's trying to do is to compile the codes that the lamp source has. You know,
but you can get to the parent code, right? I mean, the lamp code, and you can get to the for each line of this thing that you can go to a page on lamps and it'll explain exactly what it does, like the equations behind it, and then all the way down to the code. Yeah, so it's available, you know, if you want to look at it. Yeah, so it's not.
When I say I got to the instruction from the instruction page stuff and both calculate, it says make MPI or make serial. Those are two different types, I guess. It says my terminal is giving me no rule to make target serial.
Okay, we'll come to that.
Okay.
So you were showing something. I wanted to explain, like, just briefly what the lamp scripts.
Yeah.
You were showing the lamp script.
Oh, sorry.
Yes,
Okay, hold on a second.
So we talked about the initial configuration file. So lamp script, what's lamp script doing? You have the code written. It's just telling lamps, this is what I want. This is the language lamps understand to be able to interact with the code that is compiled in the background. So I will follow this sequence. So first and foremost, you're telling it you want Jones unit. So it has different kinds of units. But with the majority units, everything is related to the 612 potential. Like the distance between the.
It's a sigma,
Yeah,
sigma
it's
divided by
everything-
R.
Everything is related to that.
So it's how many sigmas?
How many, yes, everything
Yeah.
related to that.
It's like 6 sigma by R to the 6th power, sigma by R to the 12th power.
So that's what this is.
But sigma is like the atom. It's a minimum in the well, right?
Yeah.
Sigma is the minimum in the potential well. So it's kind of like the atom diameter. Or it's the interaction
Yeah, it's
distance or
related to
something.
the-
Yeah,
To the, I think the minimum distance between the.
it's the base of the well.
Yeah. the base-
Distance from
yeah,
the center to the base of the well.
Something like that.
Hmm.
So they have other units, other real units that you can use. But you know, if you're using engines. then
Yeah, I mean, you could use the sphere size as a unit, as a size unit. The sphere is smaller than the well, I guess.
Okay.
The sphere size, the bead size is the smaller than the well size, right?
Yeah. it's
In fact,
smaller
you have no
than-
bead size really, because you're just using that well to say how they interact. You just have the bead position, the center. Then that potential well, right?
Yeah.
There is no bead, it's just a spot.
Just a spot, but R is
Yeah.
like why say the radius of the bead, right?
R is the distance between beads, between spots, like Rij. In the Leonard-Jones, Rij divided by sigma. Or sigma divided by Rij to the 6, sigma by Rij to the 12.
You know, like,
I don't think there's a R for
So,
the particle.
yeah. So you can see atom style angle. That means the atoms are.
This is
bonded
for a
at an angle.
polymer, yeah, this is
So
a,
for polymer, yeah,
yeah.
they are bonded at an angle. So it can be, that atom style can be atoms, just showing that there's nothing like any bond or angle between the species you have in the system. So neighbor being is like, how I'll describe neighbor interaction with this. If in the simulation box that the atoms don't know what the positions of surrounding atoms, it will be difficult to make calculations of them. So you're putting neighbor being at 1.9, that any atoms that are related or are close to each other at the 1.9 radii, please make them neighbors. So what it does when you want to perform simulations, it breaks down the boxes into neighbors. So it keeps updating that list. So after every time step, you have new neighbors. After every time step, you have new neighbors because of the bin you specified. So that without those neighbors, that's how it keeps track of. You break them into chunks of boxes of neighbors by that bin that you specify. So by the time you move further, you will get to understand more how you can fine-tune these parameters to suit your own application, your own program. Then
That means a periodic boundaries.
okay, periodic boundary.
That means you have a mirror at the side.
Yeah.
So once it goes out, it comes back in.
Yes.
And that's the last 3 numbers, how many times it crossed. Yeah, so
Like periodic boundary, you're creating a box. Assuming we created a box of minus 50, 50, 50, 50. So X, Y, Z is 50, is a square. So we're saying periodic boundary that if the atom moves out of the box, what happens to the atom? It has to come back from the other side. Like it moves out on the positive X, you see it coming in through the negative X axis. So that's what the periodic boundary is at. You know, it's just like a mirror.
so you can, yeah, you could do it in just in X, so you could do it just in Y,
Yeah.
or you can do it X, Y, Z.
Yes.
So-
I think what other, yeah, so you can see where it says read data, initial configuration. So whatever you name your initial configuration file, that is what like you're supposed to reference it there. So you read that and you're referring the script to your initial configuration file on that line of code. Then yeah.
Oh, what, read data initial?
Yeah,
Yeah, but what about neighbor 1.9 bin?
I think I explained it.
Oh, you did? Okay.
Yeah.
Oh, I see, you already said that.
The neighbor. All
All right,
Yeah, so I think, yeah, read data. Then.
so you have to name your data file initial configuration,
Or you want
otherwise,
you have to.
which is
put the
like
exact of
this
yeah.
thing, right? Initial configuration text. So if you don't put text at the end, it won't read it.
No,
You need to have exactly, no, it's any kind of change, capital, I think, and
yeah,
small,
kind of change.
that won't work. It has to be exactly, everything has to be exact and the same. Yeah, so it's got 200 atoms, 199 bonds, 198 angles. So there's no angle between the first two because that's angles between two bonds, right? There's no bond between the first because it ends there. So there's only one. So you could have multiple bond types, multiple angle types, and then this is the box. So you say the box X low for the box, X high for the box. So it goes negative to positive. So your numbers here will be negative and positive, right? They're not on a grid, they're just freely floating, but and then the mass of atom, so you only have one atom type, the mass of atom one. If you had two atom types, it'd be 1, 2, and the mass could be different. Right? And then the atoms are listed, atom number, and then the atom position. So this is set up so the X, Y, Z. So the first one's at X1, Y1, and 0. Then all of them are at 1, 1. So they're just going along in one direction, just along the Z direction. And the second one, so this is supposed to be a polymer, right? So why is the second one negative?
So the box is defined as negative and positive. Right?
Oh, wait. This is X, Y, Z. Oh, so they aren't on, let's see. So you go, what are these numbers? We have 6 numbers, right? 1, 2, 3.
I think initial position and initial velocity.
What are the first 2
So
numbers?
first two is
No.
atom type and
Oh, atom type, and this
atom type and the
angle,
type.
angle type, maybe.
Atom type, yeah, atom or bond type.
Oh, bond type. Okay. Atom, bond type, then X, Y, Z.
Yeah,
So they aren't in a line. They aren't in a line. They're floating around like a random configuration, I guess. So they must be already kind of squiggly when it's in this. So this is already like a random walk kind of. And then it lists the velocities for the atoms. And then the bonds. So the bond, atom 1 has a bond of type 1 that bonds 1 and 2. Atom 2 has a bond of type 1 that bonds 2 and 3. That's how it goes, right?
Yeah, it's kind of
So that's how it works right on down the line.
the same thing, yeah.
Then the angles, atom 1 has a bond type 1. The angles between bond, so 1 is bonded to 2, 2 is bonded to 3. The angles between 1, 2 bond and 2, 3 bond. It's an angle between the 2 bonds.
Yeah, because
So-
we listed how many bonds.
But
you
what's
have
the,
and-
is the angle fixed in this thing? Must be fixed.
Very basic question, but are the outputs just text files or
Yeah,
will it
Yeah.
show you, it'll?
no,
like,
the output is just the same text file.
Okay, it won't give you like an animation or something.
No.
That's why you feed that text file into that
Vito.
Oviedo.
Oh.
And then it just turns it into a movie.
Okay.
And then you can change all the characteristics of the points. You can make them red balls, green balls, and make them shaded, whatever you want. Yeah, so you can do whatever you want with it after you get that. But it's just gonna read out.
Got it.
Each time you say output every 1,000 steps, it's gonna output this file. And then it's gonna combine those all into one file. So it'll have a time step at the beginning. So it's the same as this file. It's gonna have the positions and the bonds and everything.
And then you download the separate, what's it
Oh,
called?
okay.
Oh, Vito.
Yeah, so that's a shareware, which you can upgrade if you want to get added features, like things you would calculate, like the correlation function stuff.
So you want screenshots of
Oviedo.
Vito, okay.
Mhm. So, all right, back to here. So that was read. Define groups. Is this the same program?
Yeah.
That's
the
Palmer,
one,
okay.
yeah.
Time step. Let's see, where's the thing? Read initial config, then generate regular restart files to store state of simulation.
So after every 5,000 time steps, generate a file in case you want to do like, you've done your simulation.
If the computer crashes,
Yeah, or maybe you've done it 10 million times there, and you stop somewhere. You want to start to run that particular code from where you stop.
you run out of Ohio supercomputer money.
Yes.
Your $1,000 tries out.
So every 5,000 times that maybe you saw something in your data and you're like, what happened here? So is it possible to start from this point, modify the data you did and see what I can get? So every 5,000 times that write a restart file for it. So use that restart file to restart the simulation in the future if you want.
So this is just setting the clock, right? To 0.
Yeah.
And then
So that's where you find all the groups that you have. Yeah. The groups that you have in the initial configuration file, you define it there and the types.
what's a group?
Like for example, if I have sodium chloride and water in my system, so the atoms sodium and chlorine will belong to group 1, while the atoms hydrogen and oxygen will belong to group 2. They're not the same compounds, right? So that's how you group them, so that anything that is, you can tie things that could be of potential that are relative to only group 1, the sodium and the chlorine atom, and potential that are related that concern only the water, the H2O. So the interaction potentials might be different. You can define LJ for example, for sodium chloride, and define another interaction potential for the water. So this is where you do that.
Yeah, so then this is going to be the output, right? The dump
Yes,
file. So the dump command is the output that's going to go into Oviedo.
Yeah.
So dump 1. What's dump 1?
Like dump 1 is like I call it dump 2. I might decide.
Oh, it's just the name.
I can dump how many anyhow I want.
You're going to dump all the atoms.
Yeah.
Custom, we don't know what that means.
The custom means that's my, like, I want to define the parameters to dump. So I'm customizing it after every.
Oh, I see. Okay. That, and then custom means what follows it.
Yeah, what follows it.
So
After
time
every
step 1000.
Yes. So I want the dump name to be dump.dna. That's the file name. Then the ID.
That's probably
is
the
the
time
columns,
step.
Yes, the ID, the type of the atom, the position X and Y.
Oh, the ID is 1, 2, 3, 4, 5, 6.
Yeah.
The type is 1.
Yeah.
XYZ is the position.
Positions, yes.
And then these are, what are those? The times it cross the box?
Yeah, I think it's either time across the box or the velocity. I don't know.
Oh, it says below, right?
Yeah.
Image flags count how many times that are, how many move through a
Yes,
periodic
yes,
boundary.
that's it.
Okay, so that's what your file is going to go into Ovid. It's going to be a series of these
You're writing
columns,
down
like
the file.
every atom in it, the 400 atoms. It's going to list the XYZ coordinates and this, how many times they cross the border. The atom ID is going to go in. So that's all it's going to have is just a list of the positions and crossing 6 numbers for each atom, 400. And then it's going to do that again the next. It probably has a header for that, like the time step, like the time 0, 1000, 2000. So it'll be 10 of those be dumped for 10,000. Then separation start assumptions, angles.
Cosine.
You haven't done this, so you don't.
Yeah,
you know.
but so more, it's just, I think you have to give me the coefficient. So I think the 20 is like the coefficient is like the first angle 1, then 20, I think 20 degrees or whatever. Yeah, but I'm going to use the angle first off.
Oh yeah, the first one is just an index, and the
Yeah,
second one's a value.
Yeah, that's not bad.
And all the angles are angle type 1, so they're all
Yeah, so
20
those are
degrees.
angles,
He says this gives a polymer the same persistence length as DNA. Okay. I guess you just believe that. Beyond.
Yeah, now bond now, you have to create the bond between the atoms now.
So it's a harmonic spring.
Yeah.
It's gonna be x squared times the spring constant by 2 for the potential, right? Then you're gonna need to put in a spring constant. Specify bond type, type 1, spring constant, 90. The bond distance, yeah, 1.1 of the Leonard-Jones sigmas. All the distances are in units of sigma because he said that's what they were. So that's okay. And then between unbonded atoms, this is going to be like a Leonard-Jones potential, right? Like pure style. Oh, well, this is the initial when he warms it up, right? So he's going to use Leonard-Jones after the soft is a warm-up potential. So it's some other potential, I don't know what it is, but something that's easier to do. It's something that gets, things can overlap and it can separate them. Leonard-Jones, they can't overlap, I think. So basically, soft is a potential, it's a warm-up potential. It's written in the lamps code to get things to straighten themselves out. It allows, like Leonard-Jones would crash if they were on top of each other, I think. So the soft allows them to crash, be on top of each other, and it'll still run, and it'll like gently move them apart. So it doesn't, you don't have a hard crash. So this is a way to get the thing to be in a position where you could do the simulation on it. So in the next part of the thing, it'll say pair style, it'll change it for the actual simulation, right?
Are you sure they use the Leonard-Jones for this particular system?
Well, they use some other potential afterwards, I think. Yeah, I'm pretty sure Leonard-Jones. Well, I don't know for sure.
I don't think this one, I think the next one, the polymer bridge,
All right,
so number 5.
okay. These are the parameters for soft, huh? So star, does that mean it's a default or something? Then the energy is 100 KT. So the energy units are KT. So whatever temperature the system is, that many KTs. And then the cutoff, that's the distance. So your interactions only go 1.12 Leonard-Jones sigmas. So a pretty short distance. So the soft thing is just separating things out. I mean, it's just, that would be larger, I think, right? Like how far does that go for you, the distance of interaction? It's like 4 or something. Like how many sigmas do you go away to get it? Or cut off your interaction potential? Yeah.
I think it was close to 4.
Okay,
4,
so
5. I tried
so it's a small number, but 1 is a really small number.
one.
Like 1 is like this, it's only just when things are on top of each 1 sigma away, a little bit more than 1 sigma away, so that's not even an interaction. So this isn't like realistic, it's just to get the things aren't on top of each other. Variable, what's this? Seed setup fixes.
Yeah.
What does that mean? Oh, a seed for the thermostat. So the thermostat, you have to start with some temperature or something.
Yeah.
The thermostats, it's like a random number it has to start with. And you'd have to look at how thermostats work to figure that out, but you need a random number to boot the system on. So you feed in a random number. And then NVE integrator. So
I think NVT, NVE, I think for those systems, you're fixing the volume and
density.
yeah, for the other one, you're fixing the temperature and the volume. I can't remember what that one is. Let me see. That's what that NVE means.
Yeah, it's a canonical
Yes.
or grand canonical.
Fixing something.
You fix a number of atoms and the volume means it's a constant volume. And then E's, I think, the energy. Yeah, it's like canonical and grand canonical and
Yeah, MV is the velocity.
velocity.
Yeah, from the total value time integration equation.
All right, we don't know what that means, but basically it's a command.
Yeah.
Langevin equations of like
So,
mass times acceleration is
yeah. I
equal
think-
to whatever, 1/2 mv squared and
Yeah.
some other potentials.
I
It's like
think-
it's energy sum
yeah.
balance for the system. Fix all. So I don't know, there's numbers you need for that, the potentials that you need, right?
For the land environment.
Yeah, so that's what these are. And then the seed number seed, that goes back to the seed, that random number that you put in. All right, so there's a lot to this. And then where does this output to the dump file?
Yeah, you're putting the thermal details of the system after every 1,000 times.
The step number, the
Yeah.
temperature, so it's gonna calculate the temperature,
Yes.
E pair.
Energy between pair. Energy between pair of one.
Energy between molecules, the pressure and the volume. All right, so it outputs that for each run, and then it's gonna give you the position of all the atoms, so you make a movie. So you could plot, meaning you can plot the temperature versus time. Or you could plot the pair interaction energy versus time, the pressure on the volume versus time. So you get these plots to see that those things settle down over the run cycle. And then let's see, output thermal information. Output thermal information to file. Doesn't it have to say dump or something here?
It releases a separate output file.
Oh, a separate with the temperature and stuff.
So there's a dump file.
Okay.
It gives you like maybe 7 different types of files.
Okay,
after you-
okay. All right, thank you. That explains that. And setup. Oh, for the polymer, this is specific to polymers. So LAMPS has code for different things that you would do, like micelles, polymers, whatever. So this thing is some specific code. You might need to load a special code to run that, right? Like you have to load packages into it at the start.
Yeah, it's trying, I think for that one, I think it's not trying to compute the RG.
Yeah, it's trying to compute the RG for the polymer. Yeah, but this is a command, right? Compute the RG squared. So anyway, that's a package that's in LAMPS.
Yeah, or if it's not a package in LAMP, it's a user-defined package.
Yeah, but he would have to define it here, right?
He did,
Oh, he did?
yeah.
Favor are equal.
He did.
Oh, he's got like a C program or something.
Yeah, I think it's one of those, I think this is number 6, right?
Yeah.
That's not number 6.
Yeah, but this one runs perfectly fine.
Okay, that's it, right? Okay. Then it's LAMP has it. You just, LAMP has that code precompiled for it. Yeah, I was thinking of that one who added some torsion forces. Yeah, force field. So I think, yeah, Beaucage is right, LAMP has it.
So I mean, you can know if it's reached, because the rate of gyration reaches a fixed value if it reaches equilibrium. So that's another way, like you can plot the temperature, see if it settles down, pressure. But if this RG hasn't reached the expected value, like NL squared thing, RG squared should be NL squared, number of units times the step length squared, then there's a problem, I guess. And so it has to reach the value, known value of RG to reach equilibrium. Set a time, this is almost the end. Set a time step of integrator. What does that mean? 0.01 of
Yeah.
integrator.
Depending on your unit, it's your time, like the actual time step, what it is. Like,
Oh, to convert the
yeah,
one,
can be picoseconds, it can be nanoseconds, depending on the unit. But
Okay.
because we're using LJ, I think it's a relative unit. So just assuming that the time step is 0.01, then according to your system, you can do the conversions.
Oh, in order to calculate the energy, you need a time
Yeah,
step,
use the
like a
energy.
real time step.
Yeah, you convert it using all the other things relative to all the other numbers you put in the system. Yeah.
Yeah, all right, so then you, this is the warm up, you run at 5,000 steps of 0.01 each.
Yes.
And then that gives you your beginning, that's the beginning. That's, you know, you started with the thing you put in that you just had threw together. Then this soft potential lets it figure out that things aren't overlapping with each other. So run it 5,000 times, boom, it spits it out. Then it's gonna take that thing and then just go in, it's gonna now go to Leonard-Jones potential, so it redoes that potential thing. So fin A means it's a spring, like a x squared times spring constant for the energy. And it's got a cutoff to it, so it can't totally like rip apart. So it's got a fixed length that it can extend. And anyway, that's just a function that's going to use, it's built in. Bond coefficient.
Yes, all those things listed, those are the numbers.
Those are the parameters that are listed here. Bond type 1, spring constant 30. So 30 times the distance squared gives an energy. So 30 is like energy per distance squared. Or it says energy per distance squared, right? And R naught is a separation distance for the bonds. The angles, sigma, I don't know what that is. And then there's a Leonard-Jones potential. That's, so the bond between the bonded atoms is a spring, this fin A spring. And then the other interaction is going to be Leonard-Jones, and he gives the parameters for Leonard-Jones here. So that the well, let's see, so the cutoff for the Leonard-Jones is 1.12, the same thing. So that's kind of weird. There isn't a lot of interaction. It only goes out 1.12 times the well depth of the Leonard-Jones. Just the 6 part isn't having much effect. Right? It means it'll run faster. And then do a longer run, 50,000, and spitting out, it's printing every 1,000. So the first one is 5,000, and the actual run starting thing with the soft potential, then it's going to do the Leonard-Jones until it goes 50,000. Then after that, you would plot out like RG versus time, see if it reaches NL squared, plot temperature versus time, see if it reaches a fixed value, plot density versus time, pressure versus time. Everything should go to a flat number. If it doesn't, then you have to go more than 50,000, and then you go to the Ohio supercomputer. Like I want to do 1,000,000. So you set up your thing and run it on your PC and say, it's kind of doing what I think. It's kind of looks like it's going to make a liquid crystal display, like it's organizing maybe. Then you shell out the $1,000 and go to the supercomputer, or you talk to Nichols and say, like, can I use your computer to run this thing? Or you find someone else. Then you take the same code, exactly the same thing, and you feed it onto their graphic card thing, and it can run it for a lot longer without, I mean, you could run it on your laptop too, but it might take a year to kind of need your laptop for other things. So anyway, you can do exactly the same thing on a smaller computer, in other words, or you go to that Google site and you just use their thing. And you have to figure out every step of the way, like you have to figure out like how to upload your file to their system. It's going to be the same problem you're having trying to get this thing to run on your computer, right? So
You got, even just to upload the file, it's through a command.
everything's going to be like every system you use. So you've used the Ohio. So how much different was it from using a laptop?
Was it because it's a Mac maybe? It's weird.
What's the issue? Okay, ask me.
No, it's kind of designed for Mac, like it's designed for Linux. So yeah.
Person asking, is it the time difference?
No, like you say you have the code written, right? And you ran it on your computer, and then you want to go to Ohio supercomputer. What, in other words, is that a big step, or like
I didn't change any codes.
so but you have to figure out how to log on to their computer, and then like where do you put the file? And then at that point, then you have to send a command to their computer to run your file, right?
All you have to do is
But it's the same commands.
you upload your files. They'll give you your file, your drive there, you upload it on the supercomputer. Then they'll tell you how to the scripts to run theirs,
Uh-huh.
to run it, because it's their own system.
And then if it ran on your computer, it'll run there too.
Yeah.
Like there's not going to be new bugs or anything.
Simple.
All right. Yeah, so maybe you can help with it, getting that loaded up. I guess that's, I mean, we can go through the other ones, but they're the same kind of thing. And if you want to know, like,
Be able to get it. to-
yeah, Hugo can help you. We got a little bit of time. Any of these commands, like I'm trying to find one that would be,
I can start.
like if you say like read data, anything in here, you can just go to, like you can just do like read data lamps command. Everything is there, like in multiple places, but it's in the lamps webpage or. And if you go there, it'll give you the parameters, it'll tell you everything about it. I mean, so every one of the commands is listed somewhere, and if you want to do something different, you can find it there too. Like you can just Google like lamps and then like whatever you want to do. And then it'll show up somewhere. You can even find whole programs, just like it isn't like, so if you figure out how to do this, you can do like anything with it.
Do the pre-built.
That's the idea.
Pre-built lining.
Well, I wanna do 6.
Read from tiles, lamps, build, and.
That I don't know.
Yeah,
Um,
but I tried searching
So-
for it, to see if I can find it,
We'll mark.
but there's nothing.
Go back to the download.